everybody. How are we doing? It is Thursday. Woo! Busy day, busy day. Who's here for office hours right now? We had busy morning office hours. We're rebooting MuBot, getting MuBot awake in the chat. But we can work on some 320 problems, some 201 problems. What do we have? I'm going to get 201 loaded up here. I feel like we're going to have some 201 questions. What questions do you have? These are your office hours, your choice. First question goes to the first person. We'll see what people have as questions. MuBot lives in the future, and you can see the future. It's so weird. I don't understand how MuBot does that. MuBot, have you seen any questions yet? MuBot has seen no questions. Are we streaming? Are we on the internet? I do not know. One person. One person. There, I'm listening to myself. We'll see here. We should see everyone soon. We just ended class. Let me get my Pearson up in the background. If you are here, it is your turn to ask questions. Feel free to ask any questions. We'll start off with your questions. We have 2 people watching, so someone might have showed up now. Chapter 13. I'm guessing we're going to have some chapter 13. Let's see. I'm getting chapter 13 ready in the background. And let's see right here. No questions yet. Let me start working on a problem here. I might try to think of one we haven't done yet. Let's find out. I think everyone worked really hard this morning, so we might be caught up-ish, ready to go. Let's check out. So we did the nearsightedness one this morning. I do remember that one. We didn't do this one this morning. Okay. This one's not that big of a problem, but let's go ahead and do it right here. As the sample size increases, the center of the histogram will do what? Now, this problem is a theory problem. It shows you the simulations, but we can also do it theoretically. Going over here, let's talk about the simulation. Not the simulation we're in. Jokes. Matrix. So mu p hat equals to P. So what you'll notice here about this part of the equation is that the mean of the distribution is always equal to P. So the sample size will not change this. As the sample size increases right here, nothing happens to this. This is not right here influenced by the sample size. This is the mean of the distribution, and nothing at all happens to the mean of the distribution as we increase the sample size. So the distribution right here has the mean at the center, and these will be the standard deviations. They should be equal length. Let's make that look a little bit better here. So the standard deviations should be equal length right here, going up, up. I cannot draw equal length today. There we go. That's equal length. 1, 2, 3. And so what's going to happen to the standard deviation, though? The standard deviation of P, of P hat, there we go. Standard deviation of P hat is equal to P times Q over N, wait a minute, square root. So this is equal to P times Q over N square root, and the over N is going to be the important part right here. So the over N means what? This is going to stay the same, this first part. So this is going to be the same. And we want it to approximate the normal distribution, which it will. That's what the central limit theorem says, that it'll become more normal. And also it'll become tighter, which means this will decrease. And specifically, if I could spell, I said the pen is too big. So this will decrease right here. And we're talking about this right here. Now, we're saying as n increases, hey, 7 p.m., JG. Good to see you here, JG. And these simulations do show this. They do show it. So they do show it. The Kahoot will be at 7 p.m. These simulations do show it. So let's take a look right here. We see that the center of the histogram, denoted by P being at the center, will stay the same. But these standard deviations here, which are controlled by n as sample size increases, will decrease. The standard deviations right there are controlled by n to some degree. So you're going to see a smaller standard deviation to the distribution as n increases. So increase in n right here. we're going to see a smaller standard deviation. This is the important part to look at right here. The center will not change because the center is not subject to n, and the distribution will become more normal. That's one of the things that the central limit theorem says. So not that crazy of a problem, but understanding it theoretically is the important part, that the center of the histogram stays approximately the same. The distribution will become more normal, as the central limit theorem says. And also we have here that the variability will decrease. That is where we looked at over here, the variability decreasing. This is as n increases right here. That's going to make this larger, and the standard deviation would get smaller. So in theory, the curve is going to get tighter like this. The standard deviations are going to get smaller. And yes, these simulations do appear to show this. So if we look at the simulations right here, you'll notice that the center is about right here, and it stays about there. This is a weird one because the simulation's got a small sample size. And from here, it goes to 0.85 to 1, but at the end, it's going from 0.85 to 1 with very few observations in the tails. So it is getting tighter as we increase the amount of simulations, and we should get it right. We got it. There we go. Another one down. We did the predicting or the referendum today. Let's see what else we got. Did we do bank loans today? I don't recall doing bank loans today. Let's do bank loans today. People will probably check out today's videos. Check out the morning office hours if you don't see one yet. Hopefully I'll have these labeled later. I know Thursdays I teach, and then I'll try to label these right away so that way people can use them. That's the goal. Can we do the question about the construction 98% confidence interval of the true proportion? You got it, Amanda. Thank you for swinging by. You get to choose the question. You bet. 98% confidence interval. There we go. I was just doing problems because I didn't have anything to do. And so here we go. We're pulling up the questions. Without any questions to do, we jump right to the one right here. Select the correct choice. Please fill in. Can we do constructing 98% confidence interval for the true proportion? Select the correct choice below and fill in any answer boxes with your choice. Oh, wait. Did I literally just go to it? I think I just went to it, Amanda. First thing here. Lucky guess right there on which one it was. So let's go ahead and grab this right here. And let's go ahead and work the problem. This is from today's lecture and yesterday's lecture. The most recent material right here. Thank you, Amanda, for swinging by. Let's do this. So in this problem, the first thing we're going to do is we're going to mark the notation. So let's go ahead and figure out what our is, because that's going to help us with this problem. We have right here 23%. We have here 3,000 children are selected. And we have here a 98% confidence. So what is the notation in this problem? So take a moment right here. I'm going to start filling out the notation. If you're in the chat, feel free to try to take a guess at one of them. What is some of the notation? There's notation it doesn't give us, but we pretty much have everything we need. And it really helps out. Sometimes it's confusing with what it gives you. What did it give us right here? We'll use that, but not directly. We'll use 98%, but not directly. 98% is going to be for the Z star, because that's the percent confidence. And we need all of this right here for the equation P hat plus or minus Z star. And then we will do P hat times Q hat. And this will give us some tips here on what we need. So the information right here is some really good advice on what we need. So what do we have right here? So we have at least two of those right there. So we have two other bits of information. What else do we have? I'll do the more difficult one. This is P hat, the sample proportion. So if P hat is equal to 0.23, then Q hat, which is the complement, is equal to 0.77. Always remember that P hat and Q hat add up to 1. So when you're checking your work right here, look to see if P hat and Q hat add up to 1. You can always do 1 minus P hat right there to get Q hat. Make sure they add up to 1. You'll have P hat and Q hat right there. This is the sample size is 3,000. And so now we have the sample size. There we go. P hat, Q hat over n square root. And let's take a look. So now we're going to plug in our numbers here. Our numbers, well, no, we need one more thing. What is that z-score, right? Well, I know what it is because I've done way too many of these, it seems. I've done a lot of z-scores. So it is 2.3263, but we need to go to the David M. Lane applet to find this because you do not need to memorize these for the test. if this was on a test, we would tell you what the z-score is. We would say the z-score is 2.3263. MuBot's going to send us to the David M. Lane applet here in a second. MuBot, are you awake? You are awake, aren't you? There you go. Let's go ahead and grab the David M. Lane applet right here. And we need to go to the second tab. We need to go between, and then we need to enter in 98%, and we get 2.3263. And so that is the z-score. We now have all of the notation, and it says 6 right there. We have all of the notation we need to solve this. So with all of the notation, let's go ahead and start plugging in the numbers, and we'll do it below here. Okay, so p hat is 0.23 plus or minus 2.326, and then square root 0.23 times 0.77 over, and then 3,000. There we go. We got this. Have you done the question about the new restaurant seats? We can do that one after this. You got it, Ben. We did it this morning, but you're here. You get to ask the questions. So with this, let's go ahead and solve and create this interval. 0.23 times 0.77 divided by 3,000. That is now the standard error. We times it by 2.3263 is the margin of error. And we're pretty good to go. That is the margin of error right here. So I'm just putting it over it so we don't have to write it out again with my handwriting. 23% plus 1.7%, and we would do the plus or minus on this. So you would take 0.23, add to it to get the upper, 0.23 minus to get the lower. So there's the upper and the lower for this confidence interval. Let's take a look at the question and see what it wants. Well, there it is. So that's the lower is, and it wants it rounded to 3 decimals. I believe that's correct, right? Yep. And 0.23 plus this. And that's 0.248. That should be right. And just to show again how we're getting that, we are just plugging into the numbers right here. Let's show the margin of error again. This right here, everything right here, solves out mathematically to this. So the answer is 0.23 plus or minus 0.0178. So everything right there solves out to the following interval when we do the plus or minus. 23% plus or minus that, and it's as a decimal right there. Make sure to do it as a decimal. Explain carefully what this interval means. I am 98% confident the true proportion of children who are deficient in vitamin D is contained in the interval. There we go. So we are 98% confident the true proportion of children who are deficient, because that's what we were measuring, is contained in the interval. About 98% of random samples will produce confidence intervals that contain the true proportion. This goes back to the theory in the class. Oh no, I didn't put in the video the thing. I am so sorry. I forgot. Student asked if I could talk about that again. I need to do that. So this goes back to this right here where we talk about confidence intervals are made to produce the truth inside of them, and 95% of 95% confidence intervals are expected to contain the truth. And so we could say the same thing for 98% confidence intervals. 98% of 98% confidence intervals are expected to contain the truth. So about 98% of random intervals created from this are expected to contain the true proportion. We should have everything right. We do. Nice job right there. So Ben, let's hop back in. I feel really bad. I forgot. The student said, can you put in the video? And my brain, no, can't forget things. I saw that and I was like, oh, they asked if we could do that. So let's hop back over to the questions. Okay. Where is it? We've already done 2 questions? Wow. Where's my wow? Sound effects. Wow. So we'll go down here to confidence intervals. There we go. The new restaurant one, right? That might not show the version of it. No. Replace question. Put on a little music. Okay, let's find the new restaurant. We got this. Have you done the one about the new restaurant seats? This is it. Here we are. A new restaurant with 136 seats is being planned. Studies show that 58% of the customers demand a smoke-free area. How many seats should be in the non-smoking area in order to be very sure, not just sure, but very sure, that they will have enough seats in the non-smoking area. So how many seats would we need? So with this question, can you please go to the problem up? Oh, you bet. You got it, Marley. We will do that next here. So, and thank you. You can always ask a question at any time. We try to like line up the next question. So yours is the next question. If I start to get confused, just be like, hey, Brian, remember my question was next. A new restaurant with 136 seats. I'm going to highlight the notation, see if you can follow along and tell me what the notation is right here. That'll be important. We'll start drawing that out. So try to do the problems different ways each time we do them to kind of talk about it in a different way. We know that the mean of the distribution will be here. The mean will be P, and we want to go plus 3 standard deviations. So plus 3 standard deviations will vanish off the screen for a moment. No. Not leaving, we're vanishing. Not literally vanishing. And so we need to find the mean of the distribution, and we need to go plus 3 standard deviations. So finding the mean of the standard deviation is going to require some of the information right here. So we need to find, let's see right here, this is P hat, or excuse me, that's P. We switched chapters. That's the true proportion. So that is the true proportion of people who want non-smoking. They're saying that is the truth. Someone said yesterday, suppose means like this is the truth in a mathematical question. So that is the true proportion right there. Once you find P, instantaneously find Q. That's what we practice up doing. Now we need to find Q. Q is 0.42. And we find Q by doing the following. 1 minus P is Q. There's Q. Always make sure P and Q add up to 1. If you've done that properly. And P hat and Q hat are the same way. So we have here P is the true proportion. Q is the complement of the true proportion. Complements add up to 1. And now we can use our equations. So our equations are that the mean for the sampling distribution of the sampling proportion is equal to P. And that's exactly what we've drawn down here at the bottom. We've drawn this right here. And we also have that we need to find the standard deviation. The standard deviation, just one of them for P hat, is equal to P times Q over N square root. So we have this. Let's put it as a different color. Put it as green here. We want to find 3 of those. That's not green. We want to find 3 of these standard deviations and go up 3 of them. So you can see it behind me right there. We're going up 3 standard deviations. So let's go ahead and find P. Well, this is P. Okay, that's the answer. So let's go ahead and find 3, or P. And let's go here. It's 0.58, because that is just the answer. I keep saying that's the answer because it is. That's P right there. The mean for the distribution of the sample portion is equal to P. P is equal to this. And there's that right there. Wrong color. Now we need to find the standard deviation, which is going to be P times Q over N and square root of it, 136. I never learned how to draw a 3. There we go. Standard. Oh, Ben, you are so awesome right there. Great work, Ben. That does look to be about accurate. And so we're just going to double check. I trust Ben, but we're just like double checking here. So everyone can see it on the screen. Great job. Ben's going to confirm this answer. P times Q over N square root. Look at that right there. Now we're going to go up 3 of those standard deviations. We're going to go 1, 2, 3. So with this right here, have you done the question about... I bet we can do that next. No, we haven't done that one next, Amanda. We've got Marley's question, and then Amanda, we can do that one next. We're going up 3 standard deviations. We went up 3 standard deviations, and so we're literally going to have to take this amount right here and add it to this. We're going to literally take this, that 0.58, and add to it this. So we're going to be up this much from it. So we're going up 1, 2, 3 standard deviations. And so we're just going to take and add that to 0.58 because we went up 3 standard deviations. So this is just a mark of this. We'll actually, whoa. So this is at 0.706. We've got the exact of it. That is 3 of those standard deviations because we times it by 3 of these. So that was 3 standard deviations up. And that is the percent of seats we need. But I want to know how many seats we need. This is the percent of seats we need. How would I find out how many seats? You're welcome, Amanda. Thank you so much for swinging by. How would we find out how many seats we need? this is the percent or proportion of seats we need. How would we find out how many seats? You're saying, we need about 70.6% seats, 70.7% seats out of the total 136 seats. So what would you do with this number right here to find out how many seats you need? Because you're saying about 70.7% seats. So then you have the percent or proportion of seats you need out of the 136. So to find out how many seats, we're just going to multiply it by 136 because that's going to be how many seats. I was checking the number. Yep, Ben, you got it. Yep. And now here's the thing, and I'm glad it turned out this way. It's 96.14. Be very careful. What is my answer right now? So put it in the chat. I want people to realize this. This is where a mistake happens. Exactly, Haley. Great job, Haley. What do we do now that we're on this right here? We didn't have music playing earlier. I might even try to find some new songs on YouTube. We have to use like YouTube certified songs. I might even replace. There's a row of songs I don't even use. Probably replace, put new songs on here this weekend. What is the answer to this one now? This is where people make a mistake. Because they're like, I know how to do this. I've been doing math a long time. That's 96. No, that's not 96. You are correct. It does round to that. But it doesn't say round it. It says round up. That's, Haley, I'm glad you said that, Haley. Let's throw out some 50 points to chat. That's the mistake that's commonly made on this, is that we have to round up. We'll just do as Ma Pearson says. Okay, Ma Pearson, we will round up. There we go. I mean, sometimes it makes sense to round up. Think about if you're ordering pizza and you think you need 2.2 pizzas. What would you do if you estimate you need 2.2 pizzas? You say, okay, I'm throwing a party and my equation says I need 2.2 pizzas. Great job, Haley. What would you order 2 pizzas or 3 pizzas? If your equation says you need 2.2 pizzas, would you? There's different arguments to be made. You could say, I like to save money. Or you could say, I want to make sure I have enough pizza, so you round up. So this would be like being super sure, hence why I think we round up. Like, I get what they're going for. They're being like, let's round up to be extra sure. I think it was Marley's question, then Amanda's, and thank you both. So we did that one. And then Marley said, can you do the problem about the proportion of adults in a certain geographic region? Let me see, is that on this one? I don't think it is on this one. It's the next one. Okay, let's go to the other assignment here. Proportion of adults. You're welcome, Ben. Great questions, Ben. Thank you so much. I love when people are here to ask questions. That's the best part of office hours. It gives me the energy. The energy. That's what we need. That's fun, true, false. I might need a little more info on this proportion of adults one. Let's see. Is it Marley asked this? Marley, are you still here? If you have... Marley said, can you do the problem about the proportion of adult women in a certain geographic region? That's regular adults. I don't see it. We'll give it a second longer. Here we'll see. It's on sampling distributions. Sorry about that. Let me go back to sampling distributions. Okay, let me go back to sampling distributions. I was in the wrong one. Thank you so much, Marley. I should have them all memorized, right? I'm like half not joking. Is it on the homework? Did you see it? If you saw which question it was. Hey, what's up, Jonathan? Good to see you here. Did you see which one it was? If you see it, like the question number, or is it only on the homework? Sometimes there's one that's only on the homework. So if it's only on the homework, tell me that. So it's, I think it's like a proportion of adult women, he said. The proportion of adult women in a certain geographic region. Oh, it's on homework. Okay, good. Yeah, because I was like, I'm not finding it. Let's go do that homework one. We haven't done the homework one lately. 2 seconds. Remind me later. Okay. Chapter 13, homework. Okay, here we go. And here we go. Yes, we found it. We have found it. Let's do it. That one is the homework. Nice. Thank you so much, everybody. We have found the question. The proportion of adult women in a certain geographic region is approximately 49%. A marketing survey telephones 600 people at random. What proportion of the sample would you expect to be women? Okay, I want you to think of a question right here. 49% of people are women. You speak to people. What percent would you expect to be women? 49% of people are women. What percent of people, if you speak to people, don't even worry about the number back there. Don't worry about that. 49% of people are women. If you speak to people, what percent would you expect to be women? And we'll do it as a proportion, but you can say it as a percent. 49% of people are women. You speak to people. What percent would you expect to see women? So 49% are women. If you go out and speak to people, what percent would you expect to see be women? 49% of people are women. If you go out and speak to people, what percent would you expect to see women? Don't even think statistics. Just pretend this is, yep, Jonathan, you get it, yep. Pretend this is a non-stats class. What we're actually doing right here, equation-wise, we are doing the following. Mu p hat is equal to p. So that's the equation, mu p hat equals to p. And so they told us in the problem that p is 49% of people are women. And so there we have it right there, 49% are women. So this is the mean, which is what we would expect. And we have that right there. What would the standard deviation be? So once we get p, what do we need to find once we get p? Like instantaneously when you find p, you should automatically be thinking, what's this? What should we find now? I'm going to solve it. And then you check to make sure these add up to 1, to make sure you've done it correctly. What do we find as soon as we get p? What do we find as soon as we get p? As soon as we get p, we're like, oh, let's find this. Like I always think, oh, we know what p is. Let's just find what this is. Instantaneously. And they both add up to 1. Same with p hat and... I almost said it. I give away too many answers. We find q. So p and q add up to 1. They're complements of each other. Exactly. Great job, Marley, right there. We find q. So p hat and q hat add up to 1. So we take p hat times q hat over n square root. And let's go here. Bring the calculator over here. Thank you, calculator. And p hat times q hat over n, 600. Square root. It's just that the problem, someone's probably wondering, how did you come up with 600? The problem marks that it's 600 is the sample size. So p hat times q hat over n square root, it's about 2%. And let's go back to the problem. Round to 3 decimals. Got it. How many women on average would you expect to find in a sample of that size? Wait, that's a weird question. How many women on average would you expect to find in a sample of that size? This is where it gets a little confusing. So let's look at this. Okay, so what we're actually doing is we could take this mean and standard deviation over to the David M. Lane applet, and we could look at it. So what we'd be looking at right here is a distribution that looks like this. Now, I'm going to ask the question a different way. What percent of women would you expect to find in this distribution? What is the most likely percent of women to find? So what is the most likely percent of women to see? What percent of women would you expect? So once again, and it goes back to the equation, what percent of women would you expect? What percent of women would you expect to see? What percent of women would you expect to see? So when you think about it, what percent of women would you expect to see? What percent of women would you expect to see if you went out and took a sample of women? So you're saying, well, I'd expect to see about this percent on average. What percent at the very tip of the curve right here? You'd expect this percent of women. What percent of women would you expect to see in a sample? Don't even worry about the sample size yet. Just what percent of women would you expect to see? I'd expect about this percent of women. It could be a little bit less, could be a little bit more, maybe a little bit more. 49%. So what does that mean? I'd expect 49%. I'm going to go out and speak to 600 women. So I'd expect 294. This is how many, because I'd expect 49% out of 600, and it's 294. So let's go back here. I'd expect about 294 women, and that's got it. Great job. Does that make more sense right there? That's how many you would expect, which is relative to the percentage. And then we had to change it to an amount right here. So out of 600 women, I'd expect 49%. But if I'm saying how many I would expect, it'd be 294, which we're just multiplying the percent we expect by the amount. We also need to take into account the variation, because it would not be that odd. We have it here somewhere. It would not be that odd to see something like 53% women. Like 53% women is not that odd. I mean, it starts to get a little odd over here. 55, 56% women is very odd. Down here at this end, below 45% and below 43 especially is very odd. So we'd expect around 49%. And since 49% can be multiplied by the sample size to figure out how many out of 600 we'd expect around 294. And I think there was another question. Please, if you have questions, let me know, because we only have one more question ready to go here. Have you done the question about give a % confidence interval for the true proportion a staff member thinks that the true rat... Oh, and that might be 2 questions. Amanda, if that's 2 questions, let me know. There's the rat in the maze question. Came up with the newspaper predicting whether a budget will pass. Yeah, Cole, you got it. We can do that one after this. We did it earlier today, but we can do that one after this. We have the... You're welcome, Marley. Thank you for swinging by. And if you have more questions, let me know. We do as many questions as we can during office hours. So we do all the questions we can. We're going to do that one. So we got to put on more music. Nice music. And let's do this one. We don't have that many more assignments left. There's fewer assignments, but they are a little more challenging. But we had people today getting hundreds on the assignments. I was very happy. It was super awesome. End of office hours. That's why people aren't here, because they were just acing them. I was like, first person was like, I got 100. And someone was like, I got 100. And someone was like, I'm afraid to submit. I don't know if I'm going to get 100. And everyone's like, submit, do it. You got this. And they're like, I got 100. And it was awesome. Then we all cheered. And we were like, yeah. I mean, I'm actually not joking. It was actually pretty cool. Wait, where's that rat question? Am I going mad? I'm pretty sure this is a confidence interval one. Let me see. Where is that one? The question was, give a % confidence interval for the true proportion. A staff member thinks that the true rate. We find that the true rate is plausible. Okay. Not this one. Not this one. Let me go to this thing. Is this a staff member? Is it a homework one? Let me check the homework here in a second. If you're here, it's the homework. Oh, Amanda, thank you so much. Thank you so much. All the homework ones, I'm like, no. I keep thinking it's on the quiz. Let's go look at the homework one. Good question. A lot of the homework ones are on the quiz. Okay. Is it the Philanthropic organization? I think it's Philanthropic organization, right? Yep. Here it is. Okay, we got this. This is a really great question. I should have remembered this. I know this question. Okay. So this question right here is like the perfect confidence interval type question. Like, I'd love this as a test question. Like, all it needs to tell you is the Z-score 2.5758 for this. Let's talk about what we need to mark right here. This is probably one of the best questions, like just what it makes you do. So let's look at this question. Let's work it. And let's see if we can solve it. Okay, help me out with the notation, everybody here. This one gets a little bit trickier on notation. We've got that, this, and that's not going to be so important yet. Don't worry about that. I could give it notation, but I won't. I don't want to add confusion. I don't want people to write down the notation. I could give it. It's kind of a hypothesized proportion. But what do we have right here? Who wants to start us out? We just need one bit of notation to start the ball rolling. Just one thing here. which you might have even figured out. There's 1, 2, 3, 4, 5 things to figure out. 5 things! And this one down here is not something we're going to really worry about right now, notating. It's not X. I don't want to, it's not X. Just don't worry about that one. Don't worry about the one in green. Any of these notations you should know. Philanthropic organizations set out free mailing labels and greeting cards to a random sample of 100,000 potential donors on their mailing list and received, like the amount that responded, 5,462 donations. They want to build a 99% confidence interval. That's the percent confidence they want to build, which is going to tell us something else. Anything here to get the ball rolling. Who's going to get the ball rolling on any of these notations? Practicing notation is key to acing problems. You just want to look at the problem, identify the notation, and then you can identify the formula to use. So the better you are at identifying the notation, the better you are at identifying the formula to use. So we always start by identifying notation. Identify that notation, identify the equation, solve the problem. Ace the test. That's what we do. What do we have? One thing to get the ball rolling. Who's got the ball rolling right here? I'll put a 30-second timer on the clock. Don't let the timer run out. 30 seconds on the clock. Anything to get the ball rolling. Any of this notation, what is it? Who knows? What is 100,000? So what is 100,000? What is that? What is this going to be used for? Any of those things right there. Yeah, Campbell, ask away. Ask away, Campbell. We've got Cole's question. I can answer like quick questions, and then we can do like a longer one. Oh, 30 seconds up. P hat, great job, Cole. Cole, great job. Cole, you're right. That's X, and that's N, and this will be used for the Z-score here in a moment. So the Cole went ahead. Great job, Cole. Cole, let's throw some 50 points out. Cole right there figured out, and thank you, everybody. It's the practice that makes perfect. What do they mean when in the homework they're turning P hat into a Z-score? So we won't turn P hat into a Z-score. So I'll show that right here, Campbell. This might help out seeing this. P hat's always going to be found from X over N. So in this problem right here, we have 5,462 over 100,000. So we get a P hat of 0.05462. How do we then find the Z-score? Where do we need to go to find the Z-score? Just be saying it in the chat, because MuBlot's about to tell you. To find the Z-score, it's always relative to our percent confidence. So the Z-score right here is going to be relative to our percent confidence. And then we go over to the David M. Lane applet, and we go right here. And we're going to put in value from an area. And we're going to go to between. So this is a 2.5758, 2.576. So this is the Z-score relative to a 99% confidence interval. If you want a 90%, 95%, 98%, this will get wider because you're more confident and the Z-score will thus increase. Does that make sense here, Campbell? The Z-score is always relative to your percent confidence. And on the test, we would tell you an 80% confidence interval is 1.2. Oh my gosh, my brain is not on today. 1.2. Wow. 1.2816. Yep, that rounds up. 1.2816. So the Z-score down here is relative to the percent confidence, and it's the amount of area we're shading on the curve. Yeah, that's what we're doing right now, right here. So you notice how the Z-score, keep asking questions, Campbell. Yeah, any question you want us to do? We got one more in line after this, and then your question would be next, so feel free to ask. This 2.5756, 58, it's the extra decimal we don't see, is because we chose 99% confidence. 99% confidence is this Z-score right here. Doesn't matter if we use the negative or positive, because we're going to go plus or minus on this. So now we just need to we need one more thing here. We need Q hat. Q hat's always going to be 1 minus P hat. So anytime we find Q hat right here, we need to make sure it adds up to 1 with P hat. So let's find our Q hat. Our Q hat right here is going to be 1 minus P hat. So let's go over here and do 1 minus P hat. And there's Q hat, 94538. There's Q hat right there. So we have P hat, we have Q hat, and now we just need to solve the equation. So we're going to go right here and just do P hat plus or minus the Z-score times p hat q hat over n square root. And so let's plug in the numbers. This is a lot to write. 0.05462 plus or minus z-score of 2.5758 over square root 0.05462 times 0.94538 over 100,000. Now make sure to carry these through on the calculator. Make sure to carry these through. So you want to take, there's q hat right there. So we're going to times it by p hat. There we go. Divide by 100,000. There we go. Square root it. And we have now done that times 2.5758. That is now the margin of error right there. So this is the margin of error. 0.00185. 0.00185. And then we would take this. This one's only tough because of the decimals, I think. And that's got it right there. On question 3 homework, I got the first 3 parts, but I do not know how to do... Oh yeah, we'll take a look at that. Is this the one right here? Is this question 3? Is this question 3 here, Campbell? This might be question 3 on the homework. This is question 3 on the homework. You said you'll always be given the z-score on the test. Yep. You'll always be given the z-score. Yep. And so that's the margin of error right there. I'm going to times it by 100. There it is right there. So 5.462 plus this. Oh no, we lost it. Well, good thing we have it over here on the sheet. 0.00185. So 0.185, copy. 0 or 5. I'm turning this, well, there's the proportion plus this. Oh my gosh. There's the proportion. This is p hat right here, plus 0.00185. All we are doing right now, just so people can see, is we are just solving this right here for the upper, and I guess I'll draw it over here so people aren't confused, but we're solving the upper portion of the interval, which is going to be this plus this, 0.05647. I'll appear right back on the screen. And now we need to subtract it to get the lower portion. We're going to add and subtract it. So you need to add this to get the upper, and you need to subtract this to get the lower portion of the interval. So we're going to subtract that here from the lower, and so you have 0.05462 minus 0.00185, and we get 0.05277. There we go. Oh, yeah, Campbell, we can do that. We got one. We'll do that one right after this. You bet. Well, we got one more after this. 5.28. Just rounding this. You have to change it to a percentage. Please tell me if you get it wrong because you don't change it to percentage. I'll give you the points back. This has to be times by 100. That's all I'm doing right here is timesing by 100. 5.65. We should get that right. Woo! A little bit scared there. I got a little bit scared. And then do we think 5.9 is plausible? Yes or no? Just look at your interval. I am 99% confident the true proportion is contained in the interval. The one I said is also on. Yeah, let's head over there and do that. So do you think 5.9 is plausible? Yes or no? What do you think about 5.9? I believe that or I don't believe that. Campbell, so glad to hear. Yeah, it's just practice. It's a lot of practice. These are ones that, unfortunately, it's like you don't want to be cramming these the night before the test. You want to be reviewing and being like, oh yeah, that's how we do that. You know what? These are the ones we have to review. Do we think this is plausible? Given your interval, is the proposed rate plausible? Nope, not in the interval. We don't think that's really... I mean, it could happen, but probably not going to happen. It could happen, but doesn't seem likely. Doesn't seem very possible. Look, we already did 50% of that. Wow. Complete. Awesome. Let's check out... you said it was... wait, we had one more before your Campbell. One more question before. The question was, Cole asked, can you do the newspaper predicting whether a budget will pass? And then Campbell wanted the one, the first 3 on the homework. Let's do the news. Cole's waited a long time on that, so we're going to do Cole's question. I did do it earlier, but don't worry. We're We're going to practice up, and you're here live. We get to do it. And then we're going to do, so don't leave, Campbell. We'll do the other question. Okay. Look, we need music. We just need constant. Let's do this. Okay. So the budget. Aha. Here we go. We have the budget here ready to go. And so with this problem right here, so think about this. The newspaper, would the newspaper know what's going to happen in the election, or the newspaper would not know? Just think about this theoretically for a moment. Yeah, I think it's awesome. Would the newspaper know or not know what's going to happen in the election? Like, think the election's like a week away. Would the newspaper know what's going to happen or not know? Would the newspaper be like, oh, that's awesome. See, look at that. Helping out cult. They would not know. So this is like a theoretical problem, because it's saying theoretically it is true that 54% of people will vote for it. Like, that's theoretically true. So you have to take that as the truth, which is a little bit odd for this problem. So they're saying theoretically it is true that the newspaper does not know this. You are 100% correct, but this is the truth. What's the newspaper going to do to figure out what the truth might be? Like, the newspaper does not know the truth, which this is. What's the newspaper going to do to figure out the truth? They're going to take a what? The newspaper would take a what to figure out the truth? Like, the newspaper's like, well, the election's a week away, or the referendum's a week away. Let's go out and take a blank to figure out what might happen in that election or that referendum. Newspaper would go out and take a what to figure out what the truth might be, because they don't know it. They don't know it's going to be 54%. That's what's going to happen on election day. That's the truth. They don't know that. They're going to take a poll. They're going to take a sample, which means this is a sample size. Now, what we're asking is, and this is where the question is a little bit difficult, they want to know what's the possibility that in this poll, in their sample, we will see something that predicts defeat. And if we're predicting defeat, we would have to observe it in a sample less than 50%. Does that make sense? That if we saw in a sample less than 50%, that we would predict defeat? You bet. Amanda, you got it. We're going to do as many problems as we can. I think we got, your question is 2 away. Stay tuned. We'll do it here soon. We have Campbell's question, then Amanda's. I should put like a list. I should do that. That'd be cool. Like on the side, you'd be like, your question's here, and you can see it like go up on the list. Wouldn't be that hard to do that. So, we have right here. And can you do the one? Yeah, Presley, you got it. And so I think it's 4th in line now. Gotta keep them. It's like when I waited tables, I had to keep everything in my head. So what do we need to find here instantaneously? Everyone help me out. Just put it in the chat. Boom. We need to find this because we know Q. I mean, that's the answer. Since we know P, so P is equal to 0.54. So now we need to know Q. Do not worry. Someone's going to ask, how do we find Q? Q and P are complements of each other. So as soon as you know P, subtract from 1 and you get Q. Q and P will always add up to 1. So Q and P are always going to add up to 1. Exactly. And these will be P and Q because they're the truth. So we could technically find Q hat, but we don't really need to find Q hat for this one. I mean, I could, but we were concerned about in a sample observing less than 50%. So now we need our equations. We know that mu p hat, which stands for the expected mean of the sample proportion distribution, is equal to P. The variation, which is standard deviation for p hat, is equal to P times Q over n square root. So now we just need to plug in our numbers right here. Well, this is equal to 0.54. And what does that mean? That means if 54% of people are going to vote for something, well, then if we take a sample, I'd expect 54% to vote for it. Now, that's not saying we will see 54% in a sample. It's just saying on average, because 54% is the truth. So now we need to go right here and plug in the numbers. P times Q over N and square root of the quantity. I am almost blocking that. Zoom out a little bit. And plug in P times Q over N square root. We have now found the standard deviation of the distribution, which is the variation. Ooh, we can guess this one. We can guess this one. It's going to be a little tough, but we can maybe take a good guess. There's the standard deviation of the distribution, which is the variation around it. And the z-score Cool. 1.6. Which means the answer to this problem, we can guess it. It's where our brain, we got to turn on the brain. Got one more sip of coffee. Oh, we got a sip of coffee. Let the coffee flow through your veins. As the coffee takes over and takes hold, you take your guess. And you smile. No! I thought we would get it. I thought we would. Has to be close. No. Last try. Do I have faith? Oh, I don't. Oh, I'm too scared to do it. Nope. Oh, good. Still lets me guess. Okay. Let's do the actual solve on it. I was trying to guess it. Okay. So we have here the standard deviation. So good question right here, Campbell. Oh man, my brain, not enough coffee today. So here's the standard deviation. I'm trying to think through it. Yeah, I don't know. I thought I'd be close to that. So with this standard deviation right here, let's go ahead and plug this into the David M. Lane applet. And let's go over here. So we need to put in the mean and the standard deviation. Is everyone following me right now that we have the mean and the standard deviation? Does this make sense? You got 0.026? Did I round it? Yep, your answer might be close to that. You might have slightly different numbers for your P. Was your P or your sample size slightly different? Your standard deviation will be kind of similar. It just depends on your P, Q, and N. So you could have different numbers here, which will lead to a slightly different standard deviation. It'll probably be close to this. They don't change the problem too much, but this is the number we're using right here. Does that make sense? Now you need to plug it into the David M. Lane applet. So go to the David M. Lane applet, and we're going to plot below 50%. And I am shocked. This one must be very exact. Really? Really? Yep. Your sample size being a little smaller would make the standard deviation a little bit bigger. So now plug in, and your answer is going to be very close to this too. And now we take that answer and we go back to here. I think that rounded to that. 3 decimals. Is it really that exact on this one? Oh, I'd love to review the tape. How close was I? No. I had to have been so close on that. That's such a bummer. I bet I was 1 away from what it would accept. It'll accept from it'll accept up to 5.7%. I bet I put in 5.8. Did I seriously go right over it? Maybe the first time did I go from like 5 point? Nice job, Cole. I was so close in my guesses, and I was like, it has to be around there. Should have just guessed again. So I was like, everything in my head was telling me that. I did the z-score. The z-score is very close to. So if you want to find the z-score for this one, which is not a bad idea, we would take the observation of p hat, which is that right there, minus the mean over p times q over n square root. And that would equal to the z-score. So it's 0.50 minus 0.54. Hit the random music. And then we would take this over the standard deviation right here. And so we take. This will get us the z-score, which will get us the same answer. And that's what I calculated in my head. And so using that, you could do it on the David M. Lane applet this way and go mean of 0, standard deviation of 1, and below the z-score of negative 1.6. The line is in the same spot, and the p-value is nearly identical, just depending on how we do the decimals. It's still 0.055. Can you show me the David? Yep. Or are you on this right here, Campbell? Does this make sense? What I like to do is I don't change it to a z-score usually, which you can do. I go here and enter in the mean of this, the standard deviation, and then go below that area. Does that make sense? So I have here the mean, the standard deviation, and then below the area. But you could enter in, there we go. You could enter in this. This is using the z-score, This is using the actual, I call it the context, because we expect 54%. Here's the standard deviation. Here's the p hat we might observe. And then we could go through and do here. Oh, I broke it now. Oh no! No. I did break it though. There we go. So same answer. Which one did we have on the line next? Which one did we have next? This is where I start to forget who we have. Can we do the editors preparing a report for the economy? They're willing to accept a margin of error but want blank % confidence. How many randomly selected employees? So we have Amanda's question, and there might have been one before that. Amanda, which one is yours on? So we have Presley as the marketing one. So I think we have Amanda's and Presley's. Please tell me if I forgot one. So I think Amanda's is going to be on the confidence interval section. Let's take a look. Hey, wow. What do you know? First try. Let's grab this question. Okay. First try got the question, and then Presley, we will do your question next. Hopefully, I feel like there was one maybe we missed. I haven't waited tables in so long. Chapter 13, question 3, you got it, Campbell. I think that was the one we missed. We'll do this one, then we'll do chapter 13, then we'll do Presley's question, and let's do this. Editors preparing. Editors preparing a report on the economy are trying to estimate the percent of businesses that plan to hire additional employees in the next 60 days. That's nothing. Sometimes problems give you stuff that's not important. That's not important. They're willing to accept a margin of error of 2%, but want 90% confidence. Okay, so what do we got here? This is the margin of error. That's the z-score. So this right here is our margin of error. This right here is the z-score. Now, where are we going to go for our z-score? David M. Lane applet. How many employees are they looking to randomly contact? That is going to be the sample size. So the sample size is what we're solving for. So they do not give you p hat here. So you have to assume p hat is equal to this. If you assume p hat is equal to that, you assume q hat. Now, why are we doing this? Well, if we don't know what the sample proportion is going to be, we need it for the equation. We're just going to say, well, 0 is very small, 1's very big. Let's just go right to the middle and go 50%. It's just what we do. It's how we do it. It actually creates the largest. So theoretically, if any stats or math people are wanting, it actually creates the largest margin of error to use a 50-50. So you wouldn't be underestimating it. It's the most best, largest estimate we can create using 0.5. So with this right here, let's take a look. And theory aside, we have the equation p hat plus or minus z-score. And we have here p hat times q hat over n square root. Now, one thing we can do right here is we can start to solve this out a little bit, or we can start to flip this equation around. Afterwards, can we do you bet? Definitely, Amanda. Yeah, no, just keep asking the questions. We're going to try to keep them all, hopefully just remind me if I forget, or we're going to try to do as many as we can. So we actually don't need this portion right here, because this is the margin of error. That's the margin of error, and we already know it's going to be equal to. We want it to be equal to 2%. So that's the margin of error. And let's start plugging in some more numbers. We actually know what the 90% confidence interval is going to be. The 90% confidence is going to be relative to the David M. Lane applet. Let's go find Mr. David M. Lane. So 90% confidence. Where's Mr. David M. Lane? I lost you, man. On the David M. Lane applet, we need to go here and go to value from an area. Put in 90%. Go to between, and here we are. We go to value from an area, put the area we want, and we get the z-score of 1.645. So that is the z-score, and we know the other things, so let's start plugging in some numbers here and solve this. More music. 1.645. Square root 0.5 times 0.5 And we're solving for the sample size right here. So just however you want to work this can be a little bit tricky right here. We got to make sure we don't make any mathematical errors or else things are going to fall apart. So probably what I'd do is I would start moving things over. Let's move this over here. And then what I'm going to do is I'm also going to square both sides. So I'm going to square this right here. And that's going to remove out this bracket of this right here. And then I'm going to flip both sides. You can just flip both sides. Like mathematically, you can take equations. If you take both sides of your equations and you can just flip them, you can just do that. You can be like, woo! And yeah, you can hear this, woo! So you can flip both sides of these equations, and that's really going to help here because now we're going to get the following. 1.645 over 0.02 squared is equal to, and now this is on top, which is where we want to solve for it. And we're just going to take and multiply. We can just take this and bring it over here now. So, I mean, yeah, well, we got to do it. Let's go right here and write this out. We're just going to take this and multiply it over here. And that's what it's going to equal to. This is the solve. And if we look at this notation-wise, it'll help. The notation on this, which then turns this into a much easier problem if we can see the notation. So if you're here solving this right now, you can actually look at notation of it. And we have here p hat, q hat, multiplied by the z-score over the margin of error is equal to the sample size. We're solving for the sample size. Does that make sense right here? We've actually solved this out mathematically, which now it becomes like a... So, yep. And 1.645, yep, for the z-score for the 90% confidence. The z-score is always relative to the percent confidence. It's how much of the curve we are covering. So this 1.645 was found because the problem stated originally 90% confidence. So since it's a 90% confidence interval, we will then use the z-score of 1.645. Whoop, wrong screen. So there's the 90% confidence. And let's go ahead and solve it. Let's go ahead and solve this. I don't know. I feel like it's just a music day today. So I usually solve what's in the parentheses first. 1.645 divided by 0.02. Square it. What? Times 0.5 times 0.5. Really? That's quite the sample size. That's quite the sample size. If it is true, it is true. My Pearson, don't fail me now. I'm scared. Round up. My Pearson. We did it. Be very careful, carry all your decimals. That's why I usually just carry everything. We have the equations written out here. It's very easy to lose a decimal. I just carry everything out. That's why I solved it like this. So I didn't have to write everything down. I just did 1.645 divided by 0.02, which is the margin of error, squared that times by 0.5 times by 0.5, and got the sample size, and then round up. If you don't round up, please contact me and be like, hey, Brian, I forgot to round up. And I'll be like, okay, points back. So that's got it. I think we had one more from Presley, right? And then we're going to do Amanda's problem. So Presley asked... Where was it? Where was it? Where was it? I know Presley asked a question I remember. I swear I remember. Oh. It was a good while ago if it was not. Am I losing my mind? Here it is, here it is. Can you do the marketing one? I'm stuck on part B. Which one's the marketing one? Which one is the marketing one? Campbell needs help here. What's up, Alexander? We can definitely do... Which one are you working on, Campbell? Chapter 13. We'll do yours next, Campbell. I think we had Presley's been in line for a while. It's the marketing one. If we can remember which one the marketing one is, then we can do that one. Because Presley's was after Amanda's. Could you do the marketing one? I'm stuck on part B. Which one is the marketing one? Which one is the marketing one? You might have to... Is it chapter 13? Is that the marketing one? Or is that your... Is it the homework or the... So the homework remains the same every time. I think you've asked for that one for a while right now, right? Presley, if you can remind me which one the marketing one is. We got you, Alexander. We got you. We got here 26 more minutes. We can do quite a few more. It's just music day today. Music day or coffee day. That's what we do. Music and coffee all day. Okay. How does your question start, Campbell? What is this? What is the start of your question? Can we do Nearsighted? You bet. We're gonna do Campbell's question, then Amanda's, and if Presley, if you can tell me what the question is. Hey, what's up, Roger? Good to see you here. Campbell, which one is your question? She's talking about question 5 on chapter 13. Is it homework or quiz? Because it can... Here, let me pull up the quiz, or the homework. Or if you tell me the full extent of the question, that helps too to find it. Because the homework is always constant, but the quizzes can change what they are. So I think people are asking about this. This one? Mm-hmm. We did this one earlier, right? We did this one earlier. So this one is in the video. So we could come back to it later. On the interpretations, you're talking about my brain's breaking. You're talking about the check regression, right? For the check regression, make sure to give some specifics about Alexander, you got this, man. Don't worry. If you're talking about the check regression, make sure to give some kind of strong interpretations, saying whether or not the conditions are passed or failed. I think that's what you're talking about, Roderick, right? So we haven't done the nearsighted one yet. I think Amanda has a question. Which one did you want, Campbell? Because I think yours is next. And we can do we can redo a question, Campbell. Campbell, the board is yours right now. Which one do you want to do, Campbell? Because we did this one just a little while ago. We can do it again later. But which one did you want, Campbell, for us to do? Chapter 13, due tonight, question 3. And are you talking about this one right here? Is it? Yep, you got it, Roderick. Great job, Roderick. Thank you so much. Excellent work. Are you talking about this one right here? This is chapter 3 on the quiz. I mean, the homework. Just the last part, you got it. You got it. Bank problem. Let's do it. Okay. So when we do the bank problem right here, and it's good because it kind of reviews conditions also. Okay, let's take a look at the bank problem. With the bank problem, based on past experience, a bank believes, nearsighted, you got it, Lucine. Tell me if I'm pronouncing it correctly, Lucine. And based on past experience, a bank believes that 9% of people who receive loans will not make payments on time. The bank has approved 500 loans. So they are assuming that 9% is the truth, and they are doing 500 loans. 9% being the truth will be P. And as soon as we find P, we're going to find Q. So now that we know P is 0.09, Q is 0.91. So P and Q are always complements of each other. I just connected the words. So P and Q are always complements of each other right here. P and Q are always complements. And we have here the sample size. And we're good to go. So we need to know the formulas. They'll be given to us on the test. That mu p hat is equal to P. Standard deviation of p hat is equal to P times Q over n square root. So let's start plugging in the numbers. Well, for this one, the top one, it's just going to be 0.09. For the bottom one, we need to plug in the numbers. 0.09. No, we got it wrong. There we go. There we go. And so we now have the standard deviation right here, and we just need to go ahead and solve for it. Let's go ahead right here. 0.09 times 0.91 divided by 500 square root. That is the standard deviation. So we're just solving this, and 0.09 right there. Let's go back to our problem and take our numbers. So here we are, 0.09, and standard deviation to 3 decimal places. And this would round up. So there we go right there. The conditions are random, 10%, success failure. We need to randomly take these individuals. They need to be less than 10% of all people, so as long as we have 5,000 people. And we need to have at least 10 successes and at least 10 failures predicted in the sample. So we would take right here and do 0.09 times 500, and that's how many successes we expect. And then 0.91 times 500, and that's how many failures we expect. So we do have at least 10 successes, at least 10 failures. So we do pass random, 10%, and success failure. Yep, we do pass those. Now, the last part here, what is the probability that over 11%? So what you have to do here is you have to look at the problem. You just gotta like stare down. You gotta be like, hey, problem. This is not, we're gonna solve you right here. You got to think, oh, this is a tough one. I'm trying to do it in my head as we're talking. So you got to look at the problem. Okay, I see it. I see it. And so with this problem right here, you're going to look at it. And you're going to do that. Yes. There you go. You just got to look at it really hard. Okay, so what we're actually doing is we're going to the David M. Lane applet again. That's redemption right there. Redemption from the one we got wrong earlier that we tried to guess. You need to put in your mean and your standard deviation. So let's put in the mean of 0.09 and the standard deviation we found. You can carry out all the decimals, but you can put in the mean and the standard deviation. You just got to look at it really hard. Just like, Arr! Just make your brain go, I like guessing them. It's always fun to me to guess the answers. I love mental math. My brain's finally, end of office, or we got 19 more minutes, but finally my brain is working again. So in this question, it was asking, what is the probability of over 11%? So it's asking over 11% in these loans. So when we go over here to the David M. Lane applet and put in our mean and our standard deviation that we found, we want to find over 11%. So the first thing I was doing is I was trying to z-score this in my head, and I came up with a z-score of about 1.6. That looks to be about 1.6. If you want to find the actual z-score, it would be the observation minus the mean divided by the standard deviation. I was thinking about 1.6. So it rounds to 1.6, but I was thinking about what is the z-score of that? And so my brain saw this. And I do know a number that's close to this on the curve, but I was able to guess within the margin of error it would give. It looks like I was kind of close to the give it has. It has a little bit of a plus or minus on this. I got very lucky with what it allowed. It's 5.9%. I was probably it's probably 5.9% plus or minus 0.05. So I got very lucky. I should have just guessed 6%. No, Campbell, that's awesome. You can turn this into a z-score. You see how I turned this into a z-score? That's 1.56 standard deviations above. Look at this right here, the 5.91%. If you do the z-score, you can also do it with the z-score right here, and you'll get the same exact answer. So, no, great job, Campbell. Excellent work. Like, let's throw some 50 points, Campbell. I'm glad this makes a lot more sense now. That's what we try to go for here is like, let's make them make more sense. Just work on the problems, understand them, and be like, oh, we're then going to figure out the probability of above 50%. And then Lucine has the nearsighted question. I think there was one more before that. It was, everyone remind me, Amanda had one here. Afterwards, can we do the car insurance company checks police records and notes teenagers at the wheel? I think that's going to be the next chapter, right? So everyone help me out here, especially a car insurance company. It's really tough because we have 2 chapters right now. So I'm like, wait, which chapter is it? So the car insurance company notes teenagers at the wheel. Which chapter are we doing right here with the car insurance company? And great job. I want everyone to get those hundreds. Car insurance company notes teenagers at the wheel. And I think this is the next chapter. Great job, everyone, working ahead. If you ace these chapters, that's the first step in acing the test. So a car insurance company notes teenagers at the wheel. Yep, we found it. Here we go. Okay, and then Lucine, your question is next. Let's do this right here. Let's get this going. Oh, chill music. Just like chill music. Okay. We have 572 reported accidents. That sounds like a sample size to me. And we have teenagers driving at the wheel at 91 of them. Now, I do want to show this. This is where I really like statistics. This uses a slightly different calculation, but 572 and 91. 91 and 572. There we go right there. So we got that right there, and there's our interval. Solved. Okay. Let's take a look at this problem right here. We have right here that an insurance company has this amount right here. 572 accidents with 91 people, teenagers at the wheel. Let's go ahead and solve this. And drop this in right here. And there we go. So as we were mentioning, the sample size is going to be right here. That's how many accidents we recorded. And the teenagers at the wheel is this. Now we need to know the notation. Who can help me out with any of this notation, which is going to be super key right here? What is the notation we need? And I think we're building a 95% confidence interval. So 95% confidence is also going to be something we need to talk about. Here's what we're going to need down here. We're going to need all of this right here. So with all of this we need right here, what are we looking for? Or what do we have? So what do we have up there? We actually only have right now one of those things. We need to find the other ones. This is why this could be a very tough problem. It's like, wait, I've got this equation, but I don't really have any of the things I need. Any idea for any of these right now? Yep. To calculate high VIA cutoff, you'll use R squared. Great question there, Seth. Yep. You'll use regular old R squared for it. Great question, Seth. Seth, some 50 points right here. Thank you for swinging by and asking that. That's one of the best things to do. If you have a question like that, just throw it out at any time. You don't have to wait till I'm done. You can just be like, hey, Brian, for this, would I do this? And I'd say, yep, use just your regular old R squared. Great question, Seth. Thank you for swinging by. So we're going to calculate. I think people have helped me out right here. Thank you so much, everybody. It's the same chill music over and over again. I need to go to YouTube and get more songs. And people could vote on their favorite songs. That looks to be correct. It looks to be correct. And it is. It's basically 16%. 15.9. Yeah, so this is P hat right here. And P hat is equal to 0.159. And that means Q hat, which is 1 minus P hat, is 0.841. And there we go right there. So those are right there. There we go. There's P hat, there's Q hat. And we have P hat, we have Q hat, we're good to go. And once you get P hat, Q hat, make sure they add up to 1. Now the last thing to figure out here, we have P hat, we have Q hat, we have sample size. The only thing we need now is what? The only thing we need now is what to solve this. We're one step away. Just one step. We're going to call on our friend here to the rescue. Make a website named after yourself. David M. Lane, Z-Score, you're right. Great job right there. Let's go to the David M. Lane website. Mubot, where you at? Great job, Maria. We're going to go and get this Z-Score right here. The Z-Score is relative to the percent confidence, hence why we put the star on it. The star means we're picking based on the confidence level. And let's go grab the Z-Score. And we're going to go to value from an area. And we're going to go to 95%. This is not a 95% confidence level yet. And now it is because it has 95% shade in the middle. And we get the classic 1.96, a very famous number in statistics. And that is the Z-Score. So let's put the Z-Score here in purple. The Z-Score equals 1.96. Now that's the Z-Score. My brain is broken. I used all the power to make that guess earlier. The Z-score is equal to 1.96, so a Z for a 95% confidence interval is 1.96, and it'll always be that. It's basically 2. So from this point, we just put in numbers and solve. Let's go ahead and do that. So here's the solve right here. P hat is 0.159 plus or minus 1.96, the Z-score, square root 0.159 times 0.841 over 572. There we go. Let's solve. Let's do it. And here it is. Oh, we had it, didn't we? 91 divided by, there we go. There's that. 1 minus this. There's that. P times Q, P hat times Q hat over N. And then square root times 1.96. I have just found the what, and it's basically 3%. It's basically as close to 3% as it comes. What did Brian just find by multiplying all of this right here? By multiplying all of that, we have now just found the margin of error. So everything right here is the margin of error, and that's basically 3%. So I think that's about as 3% as 3% can ever get. So this is almost 16%. Can I just round that? Will it let me round that? Margin of error. Great job, Amanda. Yep, this is all the margin of error. Just solving this portion gives you the margin of error, which this is basically 3%. So let's see if this question is nice. I wouldn't do... This rounds to 3%. That rounds to 3% enough. Like this right here, everything we just solved for rounds to 3%. So the answer is going to be, when I put this in, I should put the numbers 12.9% to 18.9%. Or 0.18 as a 9. But it could be 13 to 19. We'll accept 13 to 19. Ooh, I would not suggest rounding like I'm doing. That's so close, though. It's going to get mad. No, wait. I said I wasn't going to round it the first time. And then let me check my math. I feel like something went wrong on the math. Yeah, 18.9. Good. Does it have a plus or minus? Because it's so close. We are 95% confident that the true proportion of accidents involving teenagers is contained inside the interval. So we're doing it for the confidence interval. About 95% of random samples of 572 will produce confidence intervals that contain the true proportion. A politician urging tighter restrictions says, in about 1 in every 5 accidents. 1 in 5, what is that? That's 20%. A teenager is behind the wheel. Does this confidence interval contradict the statement? Does my confidence interval here contradict the statement, yes or no? So look at my confidence interval. Some politician out there is saying 1 in every 5 accidents has a teenager at the wheel. Does my confidence interval confirm that or go against that? My confidence interval is I am 95% confident the true proportion of accidents that have a teenager at the wheel is contained in the interval 12.9 to 18.9%. So I think that's what the truth is. Somewhere between that interval. I mean, it could be outside of it, but it's probably between this interval. I think the truth is contained in this interval, 12.9 to 18.9%. A politician is saying 20%, and I'm like, I don't know about that. That's outside my interval. I'm not going to believe that. So the truth is, we think the truth is probably in this interval from the statistics to be like, the truth is probably somewhere in there. Like, it doesn't have to be. It goes against. Exactly. This goes against. Like, my interval goes against this. So we'd probably reject what that politician is saying. I like my Pearson like has an agenda. Like the interval does not. The interval does contradict the politician. The figure is outside the interval. We should get everything right. Yes, we do. Would it have accepted this? Oh, it would have. Oh, we could have just rounded it. Oh, then your interval would not go against it. My Pearson changes the context. If the interval is inside of it, or if it's inside the interval, this does not contradict the assessment. The figure is inside. So if you would choose this one right here. Does that make sense, Amanda? Great question right there. And I think Lucine's question is next. But you would choose this if the 20% was inside of here. Like if your interval went something like 15 to 21, then it would not contradict the claim. So only if you see this, or yours is 14 to 21. And so you must have seen center of your interval was like 17.5 or something. So your sample proportion. Also know how to do that because the average. So was your sample proportion? Watch this. Your sample proportion was about. Was that your sample proportion? Was that pretty much your sample proportion right there? And if your sample size was similar, then you had about 100 in your sample. So you'd probably, if as long as it's the same-ish sample size. I don't know what they chose for a sample size for your problem, but I was able to figure out the sample proportion by doing the average of the interval. Does that make sense what I did? Like imagine your friend tells you, I'm going to give you $20 to $30. How much money would you expect if your friend says, I'm going to give you $20 to $30? If your friend says, I'm going to give you $20 to $30, how much money would you expect to get? 20 to 30. That's awesome to hear. We can do the investment one. You bet. We got Lucine's question here. You would expect $25. So glad to hear that, Amanda. Swing by anytime. Ask questions. You got this. 320 question. Lastly, choose one of the two X variables in the model and interpret it correctly. What if the model I used has two X variables? Choose one of them. I guess as long as hopefully no one gets the simple model, because I want to choose one of the multiple models because they should do better. I'd hope. But yep. So choose one of those right there. And Lucine's question was Nearsighted. We haven't done Nearsighted yet. Did we do the investment website earlier today? Can anyone remind me if we did the investment website one earlier today? I need to eat more lunch. I'll go make a sandwich after this. Did we do what? Did we do the investment website one earlier today? I cannot remember. Nearsighted problem. Which one did you want to do, Emily? Feel free to ask. We got some more time. Let's put on chill music. Brian, you're in a loop. I know. Yeah, we haven't heard this song in a while. Let's do it. Beat drops right here. Can the central limit theorem be applied? So to apply the central limit theorem, we need to make sure that we have the conditions met. The conditions met are random, 10%, and success failure. So the answer is yes, we are going to apply this, but we need to make sure that we randomly select these individuals. Assumption. We don't usually try to assume that. We randomly select these individuals. We select less than 10% of the population, which 184 seems to be less than 10%, and we have at least 10 successes. That's, whoops, wrong number. This is how many successes we expect, and then the failures would be the complement of this, and that's how many failures we expect. So with assumptions, assuming that they are typical, we do meet it. Now we need to figure out, we did it earlier, but we can do it here in a moment again. The referendum one, I think we... Or maybe we did it this morning. Yeah, we could do it again. Let's do it. So here we are withdrawing the distribution. So the distribution needs to be, we need the mean and the standard deviation. So let's make the font bigger. Let's go grab the mean and the standard deviation of this. Okay. So notation. We got to practice our notation. We have this and we have this. Not much info, and it's actually like the last problem where this, well, that's not X this time. We have the sample size and we have the sample proportion. So with the sample proportion here, once we get P, you know what we're going to do. I lied. That's the true proportion. Sorry, we were doing a conference roll a second ago. So that's the true proportion because we're saying we know it. And now we can get Q right here, which is the complement of the true proportion. So we have here, you're welcome, Emily. We have here the true proportion and the complement of the true proportion. So we need to find the mean for the distribution, which is mu p hat is equal to P, and standard deviation of p hat is equal to P times Q over N square root. Did you say it? If you've done these a few, you probably said it. Got it. So let's plug in the numbers. P is going to be 0.13. P times Q over N square root. And 184. And let's see. And da-da-da-da. There we go. There's the standard deviation of the distribution, 0.038. There we go. That is the standard deviation. That is the mean of the distribution. And here's where it gets a little bit confusing because we found about 4%. So remembering that it's about 4%, let's take a look. The mean of the distribution was 13. I feel like something went wrong. The mean of the distribution was 13. And I think I did a mathematics wrong. because that seems way too big looking at the graphic. Let's try it again. You ready? P times Q over N square root. Oh, what happened? We're just going to round this right here. I knew something went wrong when I looked at those answers. So that's really great because if we do 3 of these, so let's think about that right there. We're going down about 2.5%, and look right here. We're going to take 13 and subtract from it a standard deviation, then go down another standard deviation, then go down another standard deviation, and we get that right there. Very close to it, just we didn't carry all the decimals. Or you could take 13 and add to it a standard deviation, up 1, add to it another standard deviation, up 2, add to it a third standard deviation, up 3. So these are the numbers we're seeing very, very close to. We just didn't carry all the decimals, but this is the distribution because you should note here that there are 3 standard deviations on the curve, up 1, 2, 3, down 1, 2, 3, and we found the mean and the standard deviation with the following equation right here, P times Q over N square root. And that's the standard deviation, and here's the mean of the distribution. So we have the distribution, and we would expect somewhere between 5.5% to 20.5%. Now, what does that mean for 184 children? Well, with 184 children, we would say, what's 5.5% of that? Well, that's 10, and there's the answer. Same thing goes if we talk about 20.5%. So we could go here and say, well, 20.5% of 184. I must have done something like that. And there's that answer. Rounds up to 38. And we've done it. We've done it. In the investment website. Did we do the investment website one today? Did we do the investment website? We did this one this morning. Here, we can do this one here. When we do this one right here, and then we'll end with the referendum one. So let's take a look. So help out here. You got this, Jonathan. So let's take a look at this question. Okay, with this question right here, what do we have as our random sample size? What is our random sample size? What is our random sample size? What is our random sample size? The random sample size is what? What is the random sample size? Remember, P and Q always add up to 1. Nice job, Jonathan. Thank you so much. That is the random sample size. You got it. And now we're going to take... It's 1 point... I'm losing my mind. So now we're going to take, and we're going to do mu P hat is equal to P. And standard deviation of P hat is equal to P times Q over N square root. And so let's plug in the numbers right here. So we're going to plug in 0.29 times 0.71 over 195. And there we go. And the mean is going to be P, and P is 0.029. Oh, 0.29. You rewind the tape in your head, you're like, what did I just say? Here we go. Let's find the standard deviation. There we go. Standard deviation is found. Go back here to the problem, and standard deviation goes right here, round down to 3 decimals. And then we put in the mean of the distribution, which is 0.29, and the normal curve is unimodal and symmetric. There we go. So the normal curve is unimodal and symmetric, and that's what we're doing right here by putting into things like the David M. Lane, because we put in the mean here of the following and the standard deviation, and we've actually drawn the sampling distribution. So the sampling distribution is unimodal and symmetric. For some reason, it doesn't show the last number sometimes. Does this make more sense here, Jonathan? This question is mainly about knowing how to find the mean for the distribution of the sample proportion and the standard deviation for the distribution of the sample proportion with P times Q over N square root. And you could draw this out, as we just did, and knowing that it is unimodal and symmetric, which means it's going to be the bell-shaped normal curve. And that's what we get when we meet all the conditions of random, 10%, and success failure. And you would meet the success failure condition here. I'm trying to remember what our sample size was. Our sample size was 195. So if we check the success failure with 195, we would take 29% of 195, and that would meet it. and we take 71% of 195, and we'd meet it. You're welcome, anytime. And then we had one more here. Sorry, I'm not doing them too quickly. Let's do the school referendum one. We got this. We got this. School referendum. Just before a local referendum is done, the newspaper takes a poll, and they talk to 378 people. From these 378 people, they're going to figure out how many people are going to vote for the budget. But apparently, the budget is going to get 52%, and that's probably the confusing part of the question, because somehow we already know the answer to the question. Now, we wouldn't know this in the real world. We would have a poll, and in the poll, we would see poll results. So let's go here, and although we apparently know the answer to what's going to happen, because, I don't know, we're in the future right now, we're going to think about what would happen in a sample. So if the truth is 52%, that'd make this P, and we don't know that. It's just the truth, though. We're going to ask what would happen if we saw a sample proportion that would be less than 50% and thus predict defeat. Here we have the sample size, and let's take a look at the sampling distribution. Well, we know the mean for the distribution of the sample proportion is equal to the true proportion, which is P. So the center of the distribution is 52%. And this basically means if 52% of people are going to vote for it, then, well, that's what we should expect to see in a sample. But there is variation around this, and this is equal to P times Q over N square root. And the variation is the standard deviation. It's just standard deviation's variation in a distribution. So when we solve this, we need to plug in P and Q. We don't have P net, but we do know if P is 0.52, then Q needs to be the complement of it. So Q is going to be that right there. And notice P and Q always add up to 1. So please, please, please note that. So we can plug in the numbers right here. Then we put in P times Q. Doesn't matter what order, but we'll do it in the correct order. Mathematics is awesome like that. P times Q over N square root. There we go. And here we go. Let's solve for the standard deviation. P times Q over N square root. There we go. There's the standard deviation. 0.05, 0.0256. Okay. Ooh, this is a hard one to solve in the head. This is a hard one. Ooh, not fair, my Pearson. How dare you give us one that's not going to be easily solved? We're going to, not today, my Pearson, though. Not today. We never allow my Pearson to beat us. We're going to solve this in our head, and then we're going to show how it's solved. So here we go. We get 2 attempts to solve it. Now we only need 1, right? Oh, we're not going to get it. This is a very hard one to solve in the head. Oh, last try. I know I said 2 attempts. Oh, wait, that's not going to be right. Such a hard one to solve. Okay, let's show it visually here because this one is a hard one to solve via how close it is to the center of the curve. It's less than 1 standard deviation away from the center. And how am I thinking about this right now? What is Brian seeing inside of his head? Well, let's take a look. Brian drew out the curve right here, and at the center of the curve, he put 52%, which is the mean of the curve. So at the very center of the curve, we put 52%, and then Brian is going to go down 1 standard deviation to right here, which if we round this, a rounded version of this is going to be 49.5%, which means we are interested in observing a P about here. So this is a P hat, excuse me. And that means we're interested in this probability. Maybe it's... The estimates in my head put this at about... it's going to be about 0.8. No wonder. It's going to be bigger. No, it's going to be smaller. I don't know. Maybe 23%. This is a tough one to guess. Very tough. It's more than 16%. We know that. And less than 25%. Yeah, why was I guessing those? Okay, with that information, more than 16, less than 25, probably closer to 25. We can do this. Last guess of the day. Just took 5 guesses. Should have used what I knew. Should have used what I knew after I drew this out in my head, because there's another number I know in here for the interquartile range, which let me say it was less than 25. But it is more than 16, using the empirical rule right here. It is more than 16%. Like, it has to be more than 16 because that's 1 standard deviation. So let's go ahead and put this information into the David M. Lane. Make sure you take both your standard deviation, your observed p hat, which is 50%, and you take your mean of the distribution. So we're going to draw out this exact same curve. Exact same curve is going to get drawn right here. And let's put in our mean of 50%, our standard deviation right here. We're just going to copy paste that in. And now we're going to see the drawing I made, but my David M. Lane is drawing it. And for those who need the David M. Lane is in the chat. And then we're going to go below 50%. We're going to go below 50%. And below 50%, oh, I put in the wrong mean. Don't put in that mean. See, that's why we always try to draw it out. And there's the answer right here. And I was within the margin of error. So it is 0.218, but it gave it to me, which was very nice of it. But if you look at my drawing versus their drawing, just take a look right here, and you will see a very similar drawing. So the two drawings right here are pretty similar. I'm just going to keep doing that. There's my Pearson, or here's David M. Lane, and here's my drawing with just kind of a quick sketch of what we should see. If you practice doing quick sketches like this, I think it really helps to when you have to do a problem to be like, here is what you drew and here's what the actual is. So you can then get the actual amount, and then I was able to estimate it right here. So that's got it. Whew, great office hours today, everybody. Amazing work. Really great practice. That's what we're here to do. Thank you, everybody. So many people got 100. You're welcome, Emily. Hopefully, yeah, need to go make some food. No, gosh, I think it's by Thursday. I think we're all like pretty tired. Like we're all like, oh man, it's Thursday. And I'm like, got this. That's the last bit of energy. I really appreciate you staying here, especially through the end of the problem to solve it. I'm gonna do one last thing. I need to send this to that student. Vols help vols. We're here for each other. Let's do this. There was a question in class of this. We went over this. So this notation right here. So I forgot to do this at the end of class. So if you see this, hopefully, this is the question I forgot at the end of class, because someone said, can you please cover this? So the yellow right here is the center of the interval, which comes from a sample. This is an interval we have not done yet. So I'm saying my best guess of the true proportion is the sample proportion. We have here the margin of error, which we always use. Everything after this is the margin of error. You'll notice it by the plus or minus. The margin of error is made up of two components. The z-score gives the confidence level. In later things, we'll use something like a t, but it's still the confidence level denoted by this, and it's part of the margin of error. This is just not a mathematical thing, just the words of it. The standard error here, which is p hat times q hat over n square root, is also part of the margin of error. So when you think of this right here, everything right here is part of the margin of error. Like this is the margin of error. Just like this down here is the margin of error. And this is just the words for what it is. Like both of these are just the margin of errors right here. So everything on this side after the plus or minus is the margin of error. So that's the margin of error right there. These are margin of errors down here. And the margin of error is made up of two components. How confident we are, which is later on will be a t-score. And also the standard error, which we have the equation for right here. And we won't worry about this one yet. So if this confuses you, this can just go away. We won't be covering this right now. This is not on this test. So don't let that confuse you. Which I didn't hopefully mean to cause any confusion there, but I just wanted to show how we can use this later on. Like, okay, now I'm gonna cause more confusion. In our class in BES 320, we actually do the same thing. We create a confidence interval like this right here to estimate the true coefficient of something in a model. There's our estimate, there's the margin of error, there's the confidence level, and there's the uncertainty. So we do this in 320. So 320, if you're hearing this, your confidence intervals are built the exact same way with your estimate from your sample. Then you have your plus or minus. Then you have a t-statistic, which is going to give you your confidence level. And this is all part of the margin of error. And then the standard error is just the uncertainty. It's like variation, like standard deviation. So hopefully this makes sense here that this is our estimate from a sample. Like no matter what we put right here, it's always the estimate from the sample. So this is the sample proportion. This is the sample coefficient. This right here is the plus or minus, which denotes we're starting the margin of error. Now we've entered into the margin of error. And we have the z, which is the percent confident we are. Like that'll be based on that. And then this is the uncertainty right here. So hopefully this helps out. And this is what the margin of error looks like up here. It's the plus or minus on the interval. And the center is at the very center. So if we were to draw this out one more time, let's do it in a much simpler sense. So drawing this out right here, an interval will look like this, where you have the margin of error right here. And the margin of error looks like this. It's going to be the plus or minus on the interval. So that's plus the margin of error. And this is minus the margin of error. So plus or minus. And the center of the interval is right here. So this is going to be, let's get a yellow pen. I do have a yellow pen. Good. This is p hat. And then we go plus or minus. We go plus this amount, plus a margin of error, and that everything up there is a margin of error, and we go minus a margin of error. So hopefully this makes sense right here. I need to look back on the tape and email this to that student and say, here it is. Sorry, I totally forgot. I was like, oh, we're going to start off stars. I was like, we forgot to do this. But this might be a simpler way of looking at it. I hope this helps people understand the equation and think about it visually right here. And the margin of error is half the length of the interval. One last thing I want to say on this is if your friend tells you they're going to give you $20 to $30, well, then what's the margin of error? The margin of error is plus or minus 5. And the center of the interval would be 30. Now, this is not the same kind of 25. My gosh, I can't do math. This is not the same kind of intervals we're building because we're building intervals for proportions, but still the idea remains. And we could do a proportion interval the same way to where if we said, I think the true proportion is somewhere between 0.20 to 0.30, well, then it'd be plus or minus 0.05. And so we'd go plus or minus 0.05. And at the very center of the interval would be this right here. It just makes more sense if I say your friend's going to give you $20 to $30. You'd be like, well, it'll probably give me about 25 plus or minus $5. So the center of the interval is the average of the two numbers. So just to see here visually, or we can do this right here. We made this today. It will work. Oh, no. Oh, there it goes. So if you average those two numbers, there we go. And that's the average of the two numbers right here. And then also we have right here, if we take half the length of the interval, so take upper minus lower divided by 2, half the length of the interval. Always try to think about these things in simple examples like I think the truth is between 20 to 30%. So the middle of that interval is 25, and it would be a plus or minus 5%. And this is how to understand confidence intervals with a little bit of notation. Hopefully this makes sense because we will be using this later on. But with that, let's head back to space, turn on some music. Great job, everybody. We got this. Test coming up, practice, email questions, work hard. Vols help vols. Vol means all. With that, everybody, bye for now. Bye.